everybody. We'll go ahead and get started. Consider yourself part of the Hardy group today. There was a lot of discussion during the week. Should we continue with the class given the forecast, etc.? So I gave my input saying, hey, it's probably just going to be wet roads. People shouldn't have too much trouble. But I understand weather like today can prevent some people from heading out and such. So thanks for showing up today. Today's topic, spring weather hazards. So my name is Mike Cetinich. I'll be your instructor here. My background is as a meteorologist. Got my degree from San Jose State. Spent a little bit of time while I was in college doing some flight training, mostly in tail draggers and old Taylor Craft L2. I've been at Jeppesen coming up on 35 years. I started out as an operational forecaster. I managed the operational meteorology group for about 10-15 years. Did some programming, like most meteorologists do. If you want to do anything, you got to kind of learn to deal with computers. I've been a product manager at Jeppesen for the past 15 years or so. And the bottom one there is my passion is really both aviation and meteorology. So I've gotten a great career to be able to combine those two. And I get to go out storm chasing. And once in a while, you spend hours and hours sitting in a car doing nothing, waiting for things to happen. And then you get a minute of glory where you actually find a tornado. Kind of fun when you do. So today, really, it's talking about aviation weather, help you understand weather better to make better decisions, hopefully. Pretty small group today, so please feel free to ask questions. Whenever you see anything up there on the screen that you don't understand, let's have a discussion about it. Why we're here is, weather still plays a fairly key role in a lot of aviation accidents. A lot of those are VFR-type pilots going into IMC-type conditions. So the goal is to really understand that weather pattern better so you don't become those statistics. Here's kind of NTSB statistics about the types of weather incidents that cause aviation accidents. You see winds being the #1 cause of accidents, but the fatality rate is quite low. When you get into things like low ceilings, reduced visibilities, that's where you get into the VFR-type pilot going into an IMC condition. That's where we have much higher fatality rates. In Colorado, these are from 2000 to 2009, all the red aircraft are fatal accidents. And you notice there's a pattern here. Nearly all of those are in the mountainous areas of Colorado. We don't have a lot of fatal accidents out on the plains where you have flat terrain, you got areas to land, etc. You get up in the mountains and it becomes much more challenging. Your kind of options are very limited in that terrain. So today, the first section, we're going to talk about spring weather hazards, real dynamic time of year as we can see outside today. We're going to have a couple of breaks, chances to win some weather books. Here are some trivia questions. We're going to then look at thunderstorms. So we're just getting into thunderstorm season, especially here in Colorado coming up in the next couple of months. And then we're going to do a flight scenario as our last to look at the kind of weather that you would look at as you're planning for your flight. So spring weather, meteorologically, that really starts March 1st through May 31st. It's the most dynamic time of the year from a weather perspective. We still have cold air masses to the north that are prevalent. They begin to interact with the warmer air masses to our south. We still have a pretty strong jet stream. And when those air masses collide, that frontal boundary is what the definition of that differentiation is. We still have pretty active fronts. They can cause very active precipitation, thunderstorms. We still have winter weather, as we see outside today, that can happen. And severe weather season is well underway, especially in some of the southern parts of the country. So this is 500 millibar map. So the lines are really the contours equal height, geopotential height of 500 millibar surface. And you notice the purple line is the area of the subtropical jet stream, and the yellow line is the area of the polar jet stream. That's climatologically at this time of year. When you see these red lines here, those are the kind of mean position of the upper level trough. We call them Rossby waves. They're long wave upper level troughs, and they kind of stay in one position for a fair amount of time. This would be a 5-wave pattern, which is pretty typical for the springtime. If you look at an upper level map, a lot of times in the springtime, you'll count 5 of these kind of predominant upper level waves. They're important from aviation because where those long waves exist, we tend to have a more active weather pattern. Fronts, upper level troughs, etc., we have more dynamic weather in those regions. In between those, we tend to have these upper level ridges, and that's where more favorable weather tends to exist. So this is kind of the yellow line. There's the jet stream across the United States in the springtime. We still have, in the Rocky Mountains especially, springtime tends to be kind of the wetter time of year for, especially in the central Rockies and Colorado here. March and April tend to be one of our snowier months, especially as we get into the foothills where I live. April tends to be our snowiest month of the year. And then severe weather season kicks off really in the central part of the United States. We have warm air that starts coming up from the Gulf of Mexico. That interacts with a colder air coming out from Canada and the Pacific Northwest, tend to have pretty active weather. And then the Northeast can still have some weather, although they've had their share this winter. So hopefully they're getting out of their winter season. So the hazards associated with spring weather are really thunderstorms. We talk about frontal and squall line type thunderstorms, then those tend to be the most prevalent this time of year. We get into air mass thunderstorms, those are more prevalent in the summertime, but they still can happen in the late spring especially. Icing, a day like today, if you were to actually go out flying today, you'd be encountering some icing out there. Turbulence is also very common because we still have those strong upper level and surface winds here across a lot of the country. And then also IMC. We talk about that statistic of VFR pilots going into IMC conditions, so we want to look at where that IMC exists. So thunderstorms. Really, definition is a storm characterized by which there is lightning. That's the definition of a thunderstorm. By nature, if you have lightning, you're going to have thunder. We also can get hail out of these, microbursts and wind shear, as well as very strong up and down drafts. When we talk about severe thunderstorms, we're simply talking a thunderstorm that has hail either greater than 1 inch in diameter or wind gusts at the surface of 58 miles per hour or greater. That's the definition of a severe thunderstorm. They can produce funnel clouds, tornadoes, much stronger turbulence and icing in a severe thunderstorm, stronger up and down drafts. They get to higher altitudes in the atmosphere. This here, you can see that rotation. That's a rotating mesocyclone there. You get that rotation when you get a lot of vertical wind shear, and then funnel clouds and tornadoes with those as well. So thunderstorm types, we talked about different types. Frontal and convergence lines. So that's thunderstorms that are along a convergence line. A front is really a line of convergence. You have different wind direction, we have different temperature, we have different humidity on either side of that front. And so that causes lift. As you see here, this surface right here is that front, and it slopes. The front slopes as we go back. But along this leading edge here, air is being lifted, and that's what causes the thunderstorm. The lifted air continues to rise. It's an unstable environment in this case, and we get a thunderstorm. These are much more prevalent in the spring and fall, and most of our severe thunderstorms are of this type of front. Now we also have air mass or thermal thunderstorms. So again, those are much more prevalent in the summer months where we have lighter winds, we don't have as much wind shear. And it's simply the sun is heating the ground, that's causing warm air to rise, we get a cloud that forms, and we get these thunderstorms that don't move very fast. They move maybe 5-10 miles per hour, and they usually don't become severe because we don't have the wind shear to cause the rotation. So if you take one thing away from this class, this slide is what I want you to remember. For a thunderstorm to develop and sustain, there's 3 ingredients that have to exist for that. The first one is we have to have enough lift to begin to lift the air to create a cloud. The second is we have to have moisture in the air to form the cloud. You can have lift like thermals in the desert Southwest, and you don't have a cloud. And the last one is the hardest thing here, especially for pilots to kind of grasp, is that stability factor of the atmosphere. In order to get thunderstorms, you have to have an unstable atmosphere. We'll talk more about what that means here.
Hey, Mike.
Yeah.
On the previous slide, where you were showing the graphic there for that frontal sort of formation, did that also happen orographically with a mountain range?
It can, yeah, absolutely. So lift.
We don't really see that here, being on the lee side of the mountains.
Yeah, exactly. You get fronts that are more common out of the eastern plains where you get this type of scenario. But here, when you get into the mountains, yeah, the orographic, that air rising over the mountains can have the same effect.
So that's the lift ingredient.
Exactly, exactly. Yep. So how do we get lift? So it plays right into the next slide here. So heating can be a major component of lift. You heat the ground, it becomes lighter, it's less dense, it begins to rise. So we get that typically anytime you have strong solar heating. Convergence is that, wrong button. Convergence is the next one. So these fronts and squall lines can cause that lift. We can also have things like sea breeze fronts in Florida, intersecting outflow boundaries. When you have multiple sets of thunderstorms, the outflow can intersect and create a boundary to be lifted. And then that last one, what we're talking about here, is that orographic effect. You simply have air that's flowing, it hits a mountain, it goes up, that can create lift to create a cloud.
Mike, what's a dry line, please?
Yeah, so we'll get to that in a second here. I'll show you hopefully an example a little bit later. But a dry line is simply a boundary between moist and dry air. And it occurs a lot of times out in West Texas. And that causes an initiation for thunderstorms because you typically have converging winds. You have southwest winds on the back side of a dry line. You have southeast winds ahead of it. And it creates that convergence. And this is actually right here, that drawn, that's a dry line on that front. So West Texas is kind of the key area in this country anyway, where you get a lot of these dry lines. So back behind that, you have drier southwesterly flow, and then ahead of it you have this southeasterly flow that's coming off the Gulf that has a lot of moisture. So that dry line acts as that focus of initiation of that convergence and lift. So moisture is the other ingredient we need for thunderstorms. Typically, we have to transport more moist air from, let's say, the Gulf of Mexico into other regions of the country to get that air more moist. Typically, we're looking at, for thunderstorms, we want our dew points to be about 50 degrees Fahrenheit or higher. Here in Colorado, we're a little bit unusual when it comes to a lot of these numbers because we can have thunderstorms with much lower dew points. We have such a dry environment here that we can have thunderstorms when the dew points are in the 40s, just because we just don't have a lot of moisture to work with. So we can get thunderstorms because we have so much lift here with the terrain. This here is just an example of, you have this flow that comes off the Gulf of Mexico. It can transport that moisture much farther north into the Great Plains, northern Minnesota, even into Canada sometimes. We get that air that's going all the way up there. And the last part, hardest part to understand, and I'll hopefully try to make that a little more clear today, is the stability part. So the stability of the atmosphere is defined by the rate of temperature change with altitude. We call that the lapse rate in the atmosphere. So this red line right here, the solid red line, represents the rate of temperature change with height. So the dashed line we call the dry adiabatic lapse rate. That's a standard thing in the atmosphere. It's basically 3 degrees Celsius per 1,000 feet is a rate of change. So the temperature is dropping 3 degrees for every 1,000 feet we go up. If the actual temperature profile in the atmosphere is at or less than that dry adiabatic lapse rate, we call that an unstable portion of the atmosphere. Even though this is called neutral, in meteorological terms, if we have lapse rates that are equal to that dry adiabatic, that's a fairly unstable situation. So what stability means is that if the lapse rate here is decreasing greater than this dry adiabatic lapse rate, if we lift a parcel of air, anytime we lift air, it's along an adiabatic process. So we lift air along that dry adiabatic lapse rate. So in this case here, let's say the temperature lapse rate, here's the dry adiabatic lapse rate, that red parcel, here's the actual lapse rate, which is less. So if we lift the air on that dry adiabatic parcel, it's going to go up there, and it's now going to be warmer than the surrounding environment, the surrounding temperature in the atmosphere. That means it's warmer than the surrounding air, so it's going to continue to rise. So that's what an unstable atmosphere means, is that if you lift a parcel of air, it's going to continue to rise. In the contrary here, let's say our sounding is warmer than the dry adiabatic lapse rate. It's not as steep. We're going to lift this parcel of air along this dry adiabatic lapse rate, and it's now going to be colder than the surrounding air, which means it's going to be heavier and sink back down. So you lift that parcel, it's all of a sudden colder, it's going to sink back down. It's not going to continue to rise. So we call that an unstable, a stable part of the atmosphere. So here in this section, when the temperature increases with height, we call that an inversion. It's a very, very stable portion of the atmosphere, that layer. And even here, our temperature is decreasing with height, but at a higher rate than the dry adiabatic lapse rate. So again, that's a stable portion of the atmosphere. So if we were to lift a parcel of air, it would be warmer. All of a sudden, it hits this inversion, and it's going to get colder, and it's going to stop rising. So in thunderstorm terms, we would call this area right here a cap. It means you're going to start to have lift, and all of a sudden it's going to reach that inversion and go, oh, I can't go any higher. I'm now colder than the surrounding air, so I'm going to just stay where I'm at. So that we would call this a cap in the atmosphere where thunderstorms would start to grow and then they just fall back down. So we need this kind of unstable area for that thunderstorm to keep rising. Does that make sense to everybody?
So, the way I understand it in parcel theory, there's no heat exchange between the parcel there and the surrounding atmosphere.
Correct.
So
correct.
what was easy for me to finally wrap my brain around it was to think in terms of a higher balloon.
Yeah, exactly. So an adiabatic process by definition doesn't exchange any energy or heat.
Mike, what were the ingredients a couple of days or 4 days ago that caused all that upper turbulence with even larger aircraft? A couple of them had to sit down and wait.
Yeah.
What was that?
Just really strong winds. Yeah, that was a case where we just had some very strong upper level winds that mix down all the way to the surface here over Colorado, and it just creates strong turbulence in all levels of the atmosphere. But nothing thunderstorm related. Yeah, that was just a strong wind event, which we've had a lot of this year. Okay, so stability. In a severe thunderstorm, we need the same three ingredients, lift, moisture, and instability. We just simply want stronger instability. We want more unstableness so the air rises faster. And we need this key ingredient here, vertical wind shear. And what that means is we want winds to be changing direction and speed with height. In an ideal thunderstorm environment, you have southeast winds at the surface and you have westerly or northwesterly winds aloft, so that the winds change with height, and that's what causes that storm to actually rotate. So different stages of thunderstorm development. So I changed this slide a little bit to be more in line with the FAA. So if you read the FAA handbook on weather, there's 3 stages of thunderstorm development. I've always added this 4th one up here, but that's not, if you're taking a test, I don't want you to miss this question, that's not an actual stage of thunderstorm development. I put it up there just because, hey, we can have thermals that are popping up in the air. But the real stages are, first we call it the cumulus stage. That means that we have lift, we have moisture, and all of the air in this cloud is rising. So if you're flying over a developing cumulus cloud, all of the air in the cloud is going upward. Okay, good to know as a pilot. Especially if you fly near the tops of these developing cumulus, you can get a large bump as you're going over the top of that because it's rising pretty quickly. When we get into the mature stage of thunderstorm development, we usually have a cumulonimbus cloud, and you have lift, moisture, and instability. The cloud has likely gone all the way up to the tropopause, that's where the anvil forms, and we have upward and downward motions in this cloud. We have air that's still feeding into it, creating the lift, and now we have precipitation coming down out of the cloud at a pretty strong rate. So a lot of different vertical motions. Very hazardous to fly in and near a mature thunderstorm. And then we have the dissipating stage. Once this thunderstorm has kind of lost its lift component, it all begins to come down. So we call the dissipating stage really the collapse of a thunderstorm. It loses its lift component and everything just simply collapses out of the cloud. You can still get pretty heavy rain out of a dissipating thunderstorm because all the air motion is coming down at that point. So if you fly through one of these, you're going to get a lot of downward pressure from an aviation standpoint. Okay, lightning. Obviously another hazard if we're out there flying around. Simply the electrical discharge between oppositely charged particles, either between the ground and the cloud base or within the cloud itself. From an aviation standpoint, the important fact to remember is that only 25% of lightning is from the cloud base to the ground. So if you're flying under cloud bases, only 25% of the lightning is going from the cloud base to the ground. 75% of lightning is actually up above the cloud base. Within the cloud itself, cloud to cloud, cloud to air. But you don't want to get hit by lightning. Thunder. So if we have lightning, we by de facto have thunder. So thunder is simply the adiabatic expansion of superheated air from a lightning discharge. So the lightning discharge is around 50,000 degrees Fahrenheit, much hotter than the surface of the sun. Air travels away basically in a sonic boom fashion away from that superheated air. That's what we hear as thunder. You can determine how far away you are because it travels at the speed of sound. If It's about 762 miles an hour at sea level. So basically 5 seconds for every mile away. So if you start counting, you see the flash, start counting, 5 seconds equals 1 mile away. When we get more than about 5 to 10 miles away from where lightning occurred, it's hard to hear the thunder because of just dissipation in the atmosphere, etc. So hail is another phenomenon, thunderstorm associated, that causes some concerns for aviation. Hail is created by really parcels that get recirculated within this cloud. So it starts out typically with a raindrop that gets moved back up into the colder portions of the cloud. It freezes, it gets heavy enough, it circulates back down, and it gets sucked up again, and it does these cycles. And that's what creates larger hail. The hail gets larger with each cycle that it does. It finally gets so heavy that it falls out of the cloud and falls to the ground. So typically, the stronger the vertical motions in a thunderstorm, the larger the hail is going to get.
Is there a lot of air in hail? You guys can probably say.
It depends, like everything in weather. So hail is more solid than, say, graupel. So by definition, graupel is kind of like these compacted snowballs, whereas hail usually is liquid that freezes, so it actually tends to be more solid, but there is air inside of it as well. And a lot of times when you look at a big hailstone, like I'm out storm chasing, we've seen some about 4 or 5 inches in diameter, and a lot of times they're just clumps together. So they're actually hailstones that come together and then freeze together.
Mike, what kind of wind speeds do you have to have within the cloud to be able to elevate a 5-inch hailstone
Yeah.
against gravity?
Good question. When you think about that as a pilot, it's like, wow, how does that happen? So the motions can be 5,000 to 6,000 feet per minute in a cloud that are, the lift portion is actually carrying that hailstone upward and keeping it up there. So yeah, you can have motions in a cloud that are very strong. You know, if you're just an aircraft trying to go and all of a sudden you hit 5,000 feet per minute lift, it's hard to keep your aircraft level. Yeah. And obviously you don't want to run into hail in an aircraft. So this happened to be, this is 727 flying through the Midwest at night and encountered a thunderstorm. So I'm not exactly sure why they couldn't see this on the radar, but they actually went through it. And you can see the damage to the windscreen, the nose cone, leading edges of the wings, a lot of damage from this aircraft. They were able to land safely, but not a situation you want to be in. So when we talk about thunderstorm climatology, this is the number of days per year with thunderstorms. So you can see if you follow the moisture path in the United States, really anywhere east of the Rockies, we have a better chance of thunderstorms because you have more moisture and you have better instability. Florida is kind of the key down here. 100 days a year where they have thunderstorms because they have a lot of moisture. And the convergence factor, you got air coming off the Atlantic, you got air coming off the Gulf of Mexico, it converges over the peninsula there, causes a lot of lift, and we have instability, a lot of thunderstorms. Now the West Coast, we have this big body of water out here, so we have a lot of moisture, but the key ingredient that's lacking is instability. So the West Coast tends to be a pretty stable environment, especially in the summertime. They have a large, high pressure system that sits off the coast, and it causes a lot of downward sinking air, which if you got a parcel trying to be lifted, it's not going to go very far in that environment. So that's why we don't have a lot of thunderstorms along the West Coast. Colder water, and it's a more stable environment. We talk about tornado climatology. Obviously, you know, we have this tornado alley effect right here, and that's because we have a lot of areas that come into here. We have southeasterly winds coming off the Gulf. We have northwesterly winds from these systems. Causes a lot of that vertical wind shear rotation. So we get a lot of those rotating severe thunderstorms in this region. And unbeknownst to a lot of people, we actually have a lot of tornadoes in Florida, but they're very small EF0s, EF1 type tornadoes usually. The stronger tornadoes are in this region here. This graph down here shows this is the number of tornadoes since early 1900s. So you see the number of tornadoes is increasing a lot. Why is that? Well, I doubt it's because we're actually having a whole lot more tornadoes. We simply can better detect them with NexRad radar, and we have a lot more people living in rural areas that we didn't have before, so we actually get to spot those. Yes?
I've heard once that tornadoes don't happen in the mountains, then I've heard that that was a wives' tale. now I'm looking at that, it looks like mountainous areas don't have them. Is that because we don't have monitoring, or is that because they don't have them?
No, they really have a hard time forming at higher altitudes. Yeah, part of it is terrain impact, that when you have a thunderstorm, to get that really good rotation, you need a lot of vertical wind shear. And in the mountains, the wind directions all tend to be from the same direction, so you don't have a lot of that wind shear to get that thing rotated. Now, there has been tornadoes that have been detected as high as, I think it's around 12 to 14,000 feet. In Mount Whitney, they spotted one. I think Colorado, Mount Elbert area, they actually spotted one year. But they're pretty rare because of that phenomenon. So we just don't have them. Even Colorado, obviously the greatest potential is way out on the northeast plains, where you have that better instability, better rotation, vertical wind shear. The good news is the number of fatalities from tornadoes is generally going down. So the better detection devices we have, like the NexRad radar system here in the US, we can give people more warning and get them to safety.
What's the component that, is there a component that makes Indiana kind of a
Yeah,
bubble out there?
not sure.
Is that from the Great Lakes or?
Yeah, I'm not sure what really causes that one, to be honest. But yeah, I mean, the farther north in the season you go. So typically, a lot of our tornadoes are in this region in the winter and early spring, and it moves farther north in late spring and summer.
You noticed the number of tornadoes going up. Is that because of better detection methods?
Yeah. NexRad can detect them now, so we can actually detect tornadoes on radar instead of having a human actually have to detect it. And I think we have just a lot more people living in rural areas that get to see them.
When I was growing up, the farmers used to say sometimes that tornadoes tend to follow the rivers. Is there anything to that?
I heard that too.
Yeah, I'm not sure that's the reality of the situation. It may have occurred a couple times, and then people kind of create, oh, that must be a thing that happens. There's not a great reason as to why that would occur. So icing is the other phenomenon that we have to worry about in the springtime. So icing occurs generally when you have super cold water. So water can exist at temperatures well below freezing. We call that super cooled water. When those droplets encounter a leading edge of a wing or a surface of an aircraft, come on in and find a seat, plenty of seats here, that creates icing. So that freezes on impact of the aircraft. So we tend to have clear icing, which is most dangerous because it's the heaviest form of icing, in the warmer sections, 0 to minus 5 degrees Celsius. Rime icing, which is kind of the lighter portion of icing, is in that minus 10 to minus 20, and then we get a mix in this minus 5 to minus 15. So icing can occur at even lower temperatures, down to minus 40 Celsius in thunderstorms, for example, but it's much less common below minus 20 Celsius. Most of your icing occurs between 0 and about minus 20 Celsius. Severe icing is usually associated with the presence of what we call super large droplets. Those are 40 microns or greater in diameter that are just larger, and that's why you have icing that occurs much faster. So where does icing occur? So anywhere you have lift, once again we have clouds, we have to get clouds from lift. Frontal systems provide that lifting mechanism and they form clouds. Where you have overrunning of warm moist air over like a stationary front near the Gulf of Mexico, anywhere freezing rain is present. Mountains, so we have orographic here in Colorado. A lot of our icing is associated with orographic effects from the mountains. Thunderstorms can produce icing. And then you can also obviously get icing, frost, freezing rain, and snow on the ground. So here's kind of a graph for your icing risk. So here's the temperature range, your high risk of icing. As it gets colder, the risk goes down a little bit. And you notice the temperatures are a little different between the cumulus type clouds where you have greater vertical motions and the stratiform clouds where you have a more gradual motion of air. And again, this is our kind of outside temperature range for the different types of icing. So this is a schematic of a frontal zone. So think of this as a warm front. So we have warm air kind of along that frontal boundary. Warm moist air is rising up. Anywhere you're below 0 is where we have that risk of icing. And then down below, in the colder air, we have a chance of freezing rain on that side of the warm front. This would be an actual frontal system. So here's a stationary front. This warm air coming up from the Gulf of Mexico, it overrides this front, and you have cold air on the north side of this stationary front, and that's where your risk of icing would be the greatest. Also to the north of a warm front. So when you're looking at a surface map, identify those areas as kind of your key icing type areas. Here in Colorado, it's a little different. We don't have a lot of really well-defined fronts that come through the state, so we have to look at the orographic where the temperatures are greater, less than 0. This is another surface pattern, this low here with a front, so you notice there's actual icing reports along the front and then north of the warm front here. That was the Roselawn icing incident. ATR aircraft iced up while it was holding to try to get into Chicago and came crashing to the ground because it picked up so much ice it couldn't fly anymore. So in our icing climatology, we look at, these are radiosonde soundings between November and April that showed clouds and temperatures below freezing. So you notice the Great Lakes region is kind of this prime area. A lot of cold temperatures, a lot of clouds, and the Pacific Northwest, same thing. Cold temperatures, a lot of clouds. Here in Colorado, it's really dependent, again, upon those orographic effects when we have icing. So you can also get thunderstorm-induced icing. You have the abundance of this super cold water. Temperatures can go down to -40, and the downdrafts and thunderstorms are cooler air, so you can actually have a lowering of the freezing level within the thunderstorm itself. So again, severe icing threat anytime you have thunderstorms. So any questions on icing before we go to turbulence? Okay, so springtime, wintertime is really the key for especially clear air turbulence at higher altitudes, but springtime, we still have, as we've seen in Colorado, especially the last week or so, some very windy conditions here. And that can cause low-level and upper-level turbulence. So mechanical turbulence is really below 18,000 feet, strong surface winds around terrain, so trees, buildings, hills, etc., that kind of stuff. We can get thermal turbulence and low-level wind shear anytime we have fronts, as well as mountain wave turbulence that occurs below the mountaintop level. So we can get pretty good downdrafts, we can get rotors, etc., that occur below 18,000 feet. So this is our schematic of our mountain wave. We have the mountain out here, we have air coming from the left to the right, causes that wave pattern downstream. The most turbulent region is mountaintop to the ground, and usually between the mountain ridge and this first wave pattern. That's usually somewhere between 5-10 miles downstream of the mountain range. That's our most turbulent zone, and it tends to get less turbulent with each wave downstream. You know, a picture of what it looks like a lot of times in a mountain wave. We have the cap cloud, it's spilling back in the mountains west of the divide. We can get rotor clouds at about mountaintop level, a little below, and then the lenticulars at much higher levels. Usually anywhere from about 18,000 up to about 25,000, you see the lenticulars. So above 18,000, preponderance of what we call clear air turbulence. Doesn't have to be associated with a cloud. Happens in clear air, and it's induced by vertical and horizontal wind shear, sometimes associated with the jet stream. You can also get thunderstorm-induced turbulence at higher altitudes, and mountain wave turbulence that can exist up near the tropopause and the jet stream level. So this is a schematic here of a jet stream front, if you will. The black dot there is the jet stream. That's going into the wall. So think of the air flowing in that direction. So it's perpendicular to the actual wall here. That's our jet core. Typically on the north or the cold side of a jet stream is where we have this baroclinic zone where the greatest amount of turbulence exists. Okay, in that zone there. If you're flying typically on the south side or the warmer side of a jet, the air is gradually going upward, pretty gently. It doesn't cause a lot of vertical wind shear. So you can actually have a pretty smooth flight, but you get on this cold side where that baroclinic zone is, and you can get quite a bit of turbulence. So these are a couple of aircraft that encountered severe turbulence. Normally we think, hey, turbulence really can't impact an aircraft, but in some cases, extreme cases, it can indeed. So this is a B-52. It was doing some low-level investigation. Boeing was actually flying the aircraft. It was on loan to Boeing from the U.S. Air Force. And they were flying in the lee of the Sangre de Cristo Mountains, northern New Mexico, southern Colorado. And they were 500 feet on the deck, seeing how the aircraft handled low level. They were worried about going into Russia at low level. They wanted to get the characteristics of the aircraft. 500 feet, it started getting bumpy. The captain says, hey, let's go up to 14,000, get out of this bumpy air. Well, he goes right at mountaintop level and flying just in the lee of Sangre de Cristo Mountains, and he had the tail and the stabilizer ripped off the aircraft there in the back end. They were actually able to land it back at Blytheville Air Force Base in Arkansas. They tried to go into Wichita, where the aircraft departed from, but they had a little crosswind, so they didn't want to deal with that in that configuration. And they landed safely. This one here, this was a DC-8, and you notice something kind of missing out here. So 18 feet of the wing and the outboard engine were ripped off the aircraft. And this was over Colorado, about near Evergreen, Colorado. They were coming into Stapleton. They were 30,000, and that occurred. So it was right near the tropopause, strong mountain wave situation, and this actually happened to the aircraft. They were able to land safely at Stapleton at that point. So we can also get thunderstorm-induced turbulence. So within a thunderstorm, obviously a lot of turbulence because a lot of different vertical motions. But we also get this phenomenon up here where we get this anvil. If you have strong enough flow that's coming, and you especially have a line of thunderstorms, you can actually get a wave-induced pattern downstream of that line. And we can have some pretty strong turbulence events because of that. And then lastly, we're going to talk a little IMC. So anytime ceiling is less than 1,000, enter the visibility less than 3 miles, we're in IMC conditions. We can get that from fog, low clouds, stratus, precipitation, smoke, haze, blowing sand, dust, etc. All these phenomena can create conditions where it causes instrument meteorological conditions. So fog is a ground-based phenomenon. So it happens near the ground because the ground is actually cooling the air above it. There's enough moisture in the air. It cools it, it condenses, it causes a very shallow cloud layer, which we call fog near the surface. Prime conditions is we have to have ground that's a little bit moist or a body of water. We want cool, calm, clear nights, a stable environment. So unlike thunderstorms, we want this stable environment for fog to form, which means we typically have high pressure at the surface or a ridge, upper ridge aloft, and typically it happens in valleys, lakes, coast, riverbeds, etc. So here's a satellite image. This is the Central Valley of California, which is a prime area for ground fog in the winter months. If they get rain and then all of a sudden they get cool, calm, clear nights, the whole valley kind of sets up with this fog pattern. It can be very dense. I've driven through this many times in my life. They call it Thule fog out there. And sometimes visibility down to about 100 feet. Hard to see. One time, Sacramento Airport, which is up in this region up here, actually had 30 days in a row with visibility less than a quarter mile. So it'd be kind of a depressing environment as well. So coastal stratus, a little different than fog. So fog is a ground-based phenomenon. Stratus occurs above the surface, usually of the ocean or the water. And what happens is that the air is being cooled again by the body of water, but the base of the cloud is a little bit higher. So the base of the cloud in a stratus situation is typically in this kind of a few hundred feet to maybe 1,000 or 2 feet, and that moist air underneath the inversion we call the marine layer. So it's very cool, very moist air, and then you have an inversion that caps that, and it's clear and it's warmer above the inversion. But down below that, we have cloud bases, etc. It's a great place to do IFR training. If you're out on the West Coast in the summertime, you have IMC almost every day in the morning, so a good time to do training. And the bases range again from a few hundred feet up to 800, maybe 1,000 feet. It rises and kind of lowers during the day, it moves inland at night, retreats back to the coast during the day. Typical pattern. Satellite image shows, here's that stratus kind of hugging the coast. You notice it comes into valleys a little bit. Monterey, this is Salinas Valley here, San Francisco Bay, etc. And it kind of pulses back and forth. And we'll get more into these soundings as we talk about thunderstorms a little bit later, but this is just to show the temperature and dew point very close together in the bottom layer of the atmosphere. And then you notice this large spread. It hits here in this strong inversion, and the dew point spreads out, so it gets real dry. You get above, when you pop through that inversion, when you take off out of some of these West Coast airports in the summer, it's like beautiful, clear, gorgeous, but it's really, cloudy and stuff and cool down in that marine layer type of environment. But it's a natural air conditioning phenomenon as well. So along fronts, we can also get IMC because of the lift. So this is a cold front surface. This is a warm front surface. Notice different slope. A cold front is much steeper slope than a warm front. And you have a lot more layered clouds along a warm front than you have more vertical cumulus type clouds along that cold front because of the steeper slope. And our little IMC climatology, number of days on average with IMC conditions. The more moisture you have, closer to bodies of water, we tend to have a lot more IMC. So each West Coast, East Coast, Gulf of Mexico, we tend to have more IMC as well as in the Great Lakes region. And then here in Colorado, you noticed a fair amount because of the mountains, the orographic effects that occur mostly along the divide and to the west of the divide. And if you look at our average precipitation in the country, obviously a lot more precip east of the Rockies, pretty arid environment except for Pacific Northwest here on the western side of the Rocky Mountains. And we're at our break. Any questions about any spring stuff before we move on? Yes?
Like, I think maybe 3 charts before this one, that one there. Can you just explain the distinction a little bit more? My IC is warm in the middle, cold on either side, but you were explaining some pretty significant differences
Sure.
between the two. I just didn't quite follow how to,
Yeah, so
how to make that
a
distinction.
front by definition is a boundary between two different air masses. So in this case, we would have this warm air mass in place here. And think of colder air is trying to advance and replace that warmer. So that by definition is a cold front. Along that cold front, that surface slopes at about a 1 to 50 to 1 to 75 range. What that means is that for every mile that we go up, the front is going to slope 50 to 75 miles back to, usually if we're talking about a west to east progression, that front would be sloping back to the west from where it is at the surface when you go a mile aloft, if that makes sense. That slope is what causes the air to rise. So we have usually westerly, northwesterly winds behind this in the cold air. We have easterly or southerly winds out ahead of it. And so that convergence is what's creating this cloud. And because the slope is steeper, we tend to get more vertical motion clouds along a cold front. Again, we have this warm air mass, and again, warm air is now replacing cold air along a warm front. So that's the definition of a warm front. We have warm air replacing colder air. The slope of the warm front is about 1 to 250. So now, for every mile we go up, we have to go 250 miles to intersect that front 1 mile aloft. Because it's a more gradual slope, we have more gradual or gentle lifting. We still have lift, but it's more gradual, so we have more of these layered type clouds. So if you're flying through a warm front, it's a little more dangerous from a couple of different reasons. Especially in an icing scenario, you're going to be flying through longer distances of clouds as you go through a warm front. A cold front, you're going to poke through it pretty quickly, but the clouds are going to be very vertically oriented, so you can't have thunderstorms, for example. But these layered clouds, especially if you're in an icing situation, you can be a long, prolonged period in those clouds before you get through the front itself. If that makes sense?
Thank you.
Like, just these parcels, when they rise, they are warmer. And the
so it
pressure is
depends.
lower.
Remember,
Why the cold air doesn't mix with them?
so when a parcel rises, remember, we're going to lift that parcel adiabatically along these dry adiabatic processes. So the air is being lifted along that adiabatic line. Depends what the atmospheric temperature is doing to determine if that parcel is then warmer or colder than the surrounding air.
Yeah, but it's still a lower pressure. Why the cold air, which is higher pressure, doesn't mix with it?
No. So the pressure is the same from the surface of ground. The parcel of air is at the same pressure.
Really?
Yeah. Yeah, it's really a matter of the temperature, because that adiabatic process is the conservation of all energy as it's being lifted. So there's no exchange going on.
In theory.
Yes.
I mean, there would be a small
In
amount in
theory.
reality, but it just can't mix fast enough
Yeah,
before the lifting
theoretically,
happens.
The parcel expands,
yes,
and that therefore equalizes
the pressure, correct.
Right.
Correct.
The parcel in the
You have
surrounding
expansion
atmosphere.
as you're
Right.
going to
But it
lower-
has a different characteristic.
Correct.
It retains the characteristic that it had at the surface.
Correct.
Yeah.
All right, so fun pictures you get to take when you're out storm chasing. So you get to see some fun things in the atmosphere that, before I started chasing, it's hard to understand the atmosphere and what it does when it's in this kind of mode. And it's just fascinating to see the different things that go on in the atmosphere.
I have a question.
Yeah.
Are you driving out into it, or do you wait for it to come to you?
So first you drive to it, and then you run from it. Yes. Yeah. But the key is you gotta, wherever you go, you better understand the road structure that you have, because if you have a one-way road and it's intersecting this thing, you got trouble. Luckily in Texas and Oklahoma, a lot of the roads are oriented they're on a grid, so it's pretty easy to get around. Okay, so chance to win a aviation weather book. I'm going to hand out some scrap paper. So take a couple of these, start passing these around behind you to people. Take 2 sheets if you can, that way you get questions. So if you can, write your answer, either the letter or the state here from this question, and your name, so I know who you are when we pick a winner. You got a 1 out of chance for getting this correct, and then we pick the correct answers for the book. So in 2017, past year, which state had the highest number of tornadoes reported? So every year is a little bit different. We got Georgia, Missouri, Oklahoma, and Texas. So you got 4 choices. Again, write the state name or the letter down. Either one will suffice with your name. Throw it on top of my laptop when you have a guess, and we'll pick the winner when we come back. Let's take about a 10-minute break here, and we'll come back after that.